Hi everyone, so I'm here to talk to you about integrals that I feel like are probably pretty useful for the course. So let's just get started with a relatively easy one. So what if we were considering the integral, let's go with 0 to infinity of x e to the minus x squared dx. So the first thing to do is use substitution. So we're going to set u equal to x squared. So then we have du is equal to 2x dx. I think this is where a number of people just make a silly mistake in the integration. And that's, you need to rewrite this in terms of dx. So then you have 1 over 2x du. So now if we make this substitution, we get the integral from 0 to infinity of 1/2 e to the minus u du. So this is equal to minus 1/2 e to the minus u evaluated from 0 to infinity. And of course, e to the minus infinity that's going to be equal to 0. And e to the 0 is 1. So we have 0 and 1. So therefore, we get that this is equal to 1/2. Alright, hopefully that was pretty easy for you to figure out. And next we're going to take a little detour and do a Gaussian integral. Alright, so let's consider our Gaussian integral then. And we're going to consider it over all space. So if we have the integral from minus infinity to infinity of e to the, let's give it a little constant as well, a x squared dx. So the first thing that we might find it useful to do is actually basically just say x is like a dummy variable. So if we do that, we could say that it's y, for example, or z. And actually the easy way to think about this, we're going to call this I. So the way that this problem is generally formulated is we want to calculate I squared. So this is equal to 2 of these integrals now. But if we just say it's a dummy variable, we could say that it's the integral from minus infinity to infinity of e to the minus ax squared dx times the integral from minus infinity to infinity of e to the minus a y squared dy. And then we can combine these two together. We get the integral from minus infinity to infinity go from minus infinity to infinity of, and again the integral from minus infinity to infinity of e to the minus a x squared plus y squared dx dy. So the next thing that we're going to actually do is a transformation to polar coordinates. So since this is over all space in polar coordinates is theta is between 0 and 2 pi, and the radius is between 0 and infinity. So if we want to convert this then, a conversion to polar coordinates would get us the integral from 0 to 2 pi sorry, the pen is bad. And then we have the 0 to infinity. So now if we do our polar substitution is x squared plus y squared is equal to r squared. So we have e to the minus a r squared. And whenever you convert to polar, you have to put in an extra r. So we have r dr d theta. So the really easy one to do is the d theta integral. So then we get the integral from 0 to infinity of e to the minus a r squared r dr theta evaluated from 0 to 2 pi, which is pretty easy. So you get that this is 2 pi times the integral from 0 to infinity of e to the minus a r squared r dr. So for the radial part, we're going to use a u substitution, and I'll even put it in a different color. So our u substitution here is going to be very similar to the first problem, actually. So we're going to let u be, that was a terrible a, but we're going to let u be a r squared. So then we have that du is 2ar dr, and thus dr is equal to 1 over 2a r du. Okay, so now we can use this result, and we can say that that integral now is equal to 1 over, so we originally had that 2 pi, so now those 2's are going to cancel, so we still have that pi right here on top. And then, since the 2's cancel, we just have an a, and then the integral from 0 to infinity of e to the minus u du. So this integral is something that we did at the beginning, actually. So we know that the result is just going to be what we have. We take the integral, it's minus pi over a, e to the minus u, evaluated from 0 to infinity. So this is just equal to pi over a. Right? That was what we did in the first problem. So, now we can conclude that I squared is equal to pi over a. So therefore, the integral from minus infinity to infinity of x e to the minus ax squared dx is equal to the square root of pi over a. Because remember, we squared the original integral at the beginning. So that was a pretty fun integral. So just maybe take a minute to think about that if you need to, and try it yourself, because there are lots of different creative ways to do this. And then we have one last integral I want to consider. Okay, hopefully you thought that over a little bit more. So I have one other integral I want to consider, and I think this one's kind of cool. So let's say we have the integral from minus infinity to infinity of x squared e to the minus ax squared. So right away it isn't exactly clear how to solve this, but let's actually take a look at a little trick. So I'm going to write this in a different color. So if we take a look at this, if we take the derivative of the exponential with respect to a, we get minus x squared times that exponential back again. So if we took the minus dda of the exponential, we're going to get x squared e to the minus ax squared back. So we're going to use that little trick in solving this integral. Alright, so we can use this trick. So this is equal to minus dda, the integral from minus infinity to infinity of e to the minus ax squared dx. But we already solved this in the last problem. So we know that this is equal to minus dda, and this integral is just the square root of pi over a. So maybe an easier way to see this, so we have minus dda pi, and then a to the minus 1/2. So this is equal to the square root of pi times 1/2, and then if we're subtracting a power, a to the minus 3/2. Okay, so hopefully that made sense. So now we can conclude that the integral from minus infinity to infinity of, the pen's being poor, x squared e to the minus ax squared dx is just simply equal to the square root of pi over 2a to the 3/2. And that's what I like to call some useful integrals and tricks that weren't exactly obvious. So thanks for watching. I hope you learned a lot, and if you have any questions, feel free to reach out to me. So that's all for the useful integrals part of quantum and Pchem. So hope you enjoyed.